Welcome to the dojo, ninjas! I'm Sensei Dave, and let's take this ugly-looking derivative problem and absolutely crush it with the implicit differentiation method. Now, why am I using implicit differentiation? This e to the xy and sine of y makes it really difficult or near impossible to write this equation as y equals something. So that's a hint to use implicit differentiation. And before I show you how, a little bit about me, a random ninja on YouTube. I used to tutor students just like you back in college when I was taking calculus, and I'm a software engineer who makes fun apps like the Ninja math game you can check out in the description below. But without further ado, let's get into why you came to this video. The first thing with implicit differentiation, you take the derivative of both sides of the equation with respect to x like I did here. And then it's nice because if you remember with derivatives, a derivative of an expression in parentheses allows us to rewrite this now as a sum of separate derivatives. You want to break things in parts that are easier to work with. Now, the right-hand side of the equation is easy because you are taking the derivative with respect to x of terms that only have an x in them or are just constants. But then we're going to have some fun with this e to the xy here because this one's a complicated term. I'll get to that in a bit, but let's start with the right-hand side first and work our way from the easier parts to the harder parts. The derivative of x squared was 2x, and the 3 went away, so now we end up with this on the right-hand side. Now the next term I want to work with is this sine of y. Now remember, and for a second I want you to pretend it's an x. How would you take the derivative? It would just be cosine of x, right? But because we have a y here, but we're taking the derivative with respect to something else, which is x, take the derivative like you normally would, so cosine of y, but then times dy over dx. You have to have this differential here because the expression did not have an x in there. Now, what I want you to work on next is with this e to the xy term, think to yourself how we can make this easier because the product within a power is a little bit difficult, right? If you don't see it, that's okay, and you don't have to do this, but it makes it easier to break this down. You can go ahead and let a new variable u equal that power, xy. And the idea now is if I rewrite the expression as e to the u, it becomes more obvious that we can now use the chain rule and work with something that's very clean, right? Because the derivative with respect to x of e to the u is just going to be e to the u itself times the derivative of its power with respect to x, this du over dx. And now what you can do is you can plug back in what u is, which is xy. And so you end up first with this part here, which is done. And now what's nice is xy, when you take its derivative, it's no longer in a power of e. We flattened it because now we just got to do a simple product rule. And product rules are nice with terms like this because if you remember, you just simply take the derivative of this x first, which will just become a 1, times the y, and then you're going to take the derivative of the opposite, right? You're going to now have the y terms derivative, which makes it go away, times x. But remembering now that because you took a derivative of y with respect to x, you cannot forget this dy over dx here. It's again left over. And so what I want to do is put this back into the expression we're working with now. And the goal of any derivative problem, like we're seeing here, is you have terms that either do or do not have dy over dx. But the answer is going to be done when you have dy over dx equals something, right? That's a classic derivative. But what we can do is manipulate the expression by multiplying this e to the xy through. And then the goal is to get dy over dx terms by themselves, right? And then factor them out. So I multiplied the expression on the left through. And then what I want to do now is subtract y e to the xy on both sides, giving me this new expression on the right-hand side here. And then what I can do is factor out dy over dx. And this is starting to become more clear on what the answer might look like, right? Because now when I divide both sides by this part, what I'm going to end up with is dy over dx equals this expression. And you might be wondering, is this okay on an exam to have an answer like this? Well, yes, you don't have to have an answer that's only in terms of x, because this was what's called a transcendental function. You can't really just easily write this with elementary functions as dy over dx equals something all in terms of only x. So you can even try this for yourself, graph the original function. it's not going to be really clean to work with. And here's your homework exercise you can leave in the comments below. Tell me what the domain of this derivative function is.